of all, it's Helisam, which is kind of local here, but there's also some aspects of time domain inversion that are kind of like lessons to be learned from here. So there's some depth in here. So first of all, what are we looking for? We're looking for massive sulfides, kind of a geologic cartoon of the development of this. There's the sulfides end up being in these sort of stringer zones, and there's different regions. So there's a zinc rich, a gold rich, and a copper gold rich. And so each of these kind of exists at different depths. And importantly, they're down at significant depth. They're a kilometer-ish. So, what are our properties? Just to keep it simple, basically it's volcanic background. Don't you wish you had that here? 1,000 ohm meters, and you got sulfides of 1 ohm meter, and as I say, they kind of exist in these stringer zones. So Helisam, the transmitter is actually a loop that has existed there for many years, and it's used by a whole bunch of experiments. There were some people who were talking about squid magnetometers. We've actually inverted 3-component squid magnetic data from this to try to find the sulfide deposits. Lalore is a test site. I think there was a whole symposium on Lalore, and I think there were 12 or 13 different types of EM surveys that were carried out there. And so it makes it pretty interesting, and then when you talk about, people know what you're saying. So here's the transmitter in red, a couple of kilometers on the side. And the receiver is a total field magnetometer. It's a cesium vapor magnetometer, and time channels from 0.42 to 27 milliseconds. And here's the flight lines in blue. So the data, so these data are total field magnetic data. So that's what you manage. Total field is composed of the Earth's field and plus the anomalous Earth's field. So this is any susceptible material inside that's being magnetized by the Earth. So, and generally, when you do a mag survey, that's what you're interested in. In this particular case, there's another EM field, and that's coming from the EM induction from this loop. So you measure this, and then to try to find an anomaly, you take the absolute value of this. You're measuring total field. So you subtract off the Earth's field. So that leaves you with the anomalous field plus the EM projected onto the direction of the Earth's field. So again, these guys are small compared to the Earth's field, so just the same as in magnetic surveying, you're just getting a projection. So then you do this, but then you change the polarity on your transmitter, and then you subtract the things, and you end up with an anomalous data that's actually the electromagnetic induction, but projected onto the Earth's field. Right? So just the same as in regular magnetics, where you measure the anomalous field projected onto the Earth's field. Now we're actually measuring the BEM. Okay. So here's the data maps at different time channels. So here at early time channels, 0.42 milliseconds, here's the loop transmitter. And look at this guy here. So he's really highly conductive. There's high signal right along here. At later times, it kind of looks like this. So there's early times and there's later times. And the question is, okay, what do you do with that stuff? And typically what has happened is the recognition that these early time data are somehow connected with geologic noise or infrastructure or something, and so we just kick those out and invert the late time data. So that's usually what happens. Just work with the late time data and go ahead and invert. One of the things, at least to me, was kind of involved with the inversion of the data. Is in most cases, when we invert data, we just start with half space, right? And then off you go. Turns out in this case, that doesn't really work very well. And the reason for that is, and you already have some understanding about why occur. Okay, I think you do. Hopefully. So I've done my job, you do. So remember, so here's our loop. And so you've got currents that are kind of flowing in through there. So if I turn those currents off, then I'm going to get currents in the earth that kind of diffuse outwards. And that's kind of your starting position. And then you're going to try to build something up inside that has got some kind of signal. But the reality is that there's, all your currents in the earth are kind of going around like this. But if you've got something, conductive bodies in here, you actually want to have vortex currents that are somehow going in here. So you don't have any of those. And so it's difficult for the inversion algorithm to kind of get some traction and get started. So that means what you need to do is to have some kind of a warm start. You need to have some kind of conductive material in here, and then the inversion algorithm, which is always a gradient thing, gets like, okay, I got it now. So to get a warm start, we used a program that I think people are familiar with. It's called Maxwell, and it generated a couple of plates, and we just made those plates into a couple of prisms. And so we start off with something that looks like that. And then that goes into the inversion algorithm. And the result of it is we end up with a three-dimensional conductivity model, again, done the same way as we talked about before, that looks like this. So this is kind of a cross-section. And but this depth plane here is at 1 kilometer. So we're seeing like a conductivity complex here at a kilometer depth. So that's great. So we use the lifetime data in this structure. However, if we look at the surface, kind of look at the conductivity that's near the surface, you see that there's actually what's going on. Question or what? Now, if we inverted the earlier time channels, however, we might be able to do something. And so what we want to do is kind of investigate, what's the effect of throwing away those early time data? And this stuff that we see up here, is that really cool, or is that just because we didn't have we data that were kind of associated with that, and that's just kind of an artifact. So now let's do something different. Let's take the early time data only and invert them. If we do that, we find that there's this high conductivity that's running right along here. And that's basically a power line. So you got a power line that's running in through there. And then there's a few other things that are just basically local infrastructure. So there's some conductive sheds and pipes and stuff like that. But if you invert the early time data, then you get this. And that's very different than what you'd have had as far as what you think is at the surface just by inverting the late time data. So now we can put everything together, and this is how we do it. So we've inverted the early time data, and for that you need high resolution, so you make really small cells, fit those data well, and we get some kind of a structure. So we take that structure and we put it in as a reference model for the full inversion. And the other thing that we put in as a reference model is that kind of warm start blocks. So what we're going to do is to do the inversion of all the time channels, some near surface stuff that's kind of built into a reference model, and also some deep stuff, and then you let it go. And what you see is that there's a deep conductive packet down here. There's a near surface infrastructure. You basically got rid of a lot of that other stuff that was there. And one thing that's kind of interesting about that, there's a near vertical conductor here that's offset from the main packet. That was really of interest. And that has been drilled and actually found to be a sulfide. As far as a synthesis, by doing things kind of carefully in that manner, a little bit of a step-by-step process, we get something that looks like that. What we're seeing here, it's probably a little obscure to you, but that's actually kind of like an isosurface of the mineralization that's obtained from drilling. So it kind of overlays on that. And as I said, this is a packet that was recently drilled and found out to be a sulfide. So I think there's a couple of takeaways here. One is that the early time data actually constrain information about what's going on in the near surface, and it definitely improved the inversion for the late time. And that in some cases, a warm start is actually beneficial or negative. Yeah. So we won't go through this, but this is, again, another sulfide deposit, looking for this, a number of different types of surveys of meso-lamass, which once they found it, through BTEM, explored a bit more with meso-lamass, did some ERT, just trying to figure out which survey they wanted to use, whether a tour ram or a sling ram, and then decide on one of these and then get some borehole time domain EM. So that kind of process might resonate with people. Anybody done meso-lamass? What was the search test?
I did it in Porsche on a gold deposit in South Australia. And we were doing, we tried borehole, inciting it in borehole and doing surface, and we were trying some sort of cross-hole, borehole, meso-lamass style. Well, we were calling it applied potential. It was easy to spell.
Okay. Was it informative?
It was indicative, because you got the potential fields were elongated in the orientation of the strike of the mineralization, but from a targeting point of view, no.
Okay.
We didn't model it.
Yeah, so he eventually decided on tour ram and started to look at stuff that was possibly off hole, extended the hole, and found stuff very useful. Okay, so what I want to do now is to switch gears, and we're going to go to, so we're done time domain, let's go to frequency domain. So principles, again, are exactly the same. We've kind of been over this. Now we're going to, again, do a vertical magnetic dipole, but in the frequency domain. So you already know what's going to happen here, right? So we have the vertical magnetic dipole, the currents are going to be circular, kind of look like that. Now we're going to take the absolute value of the current, so it's going to be yellow and yellow. Magnetic field, it's going to look like that. We're going to measure up here. Fields can get complicated, especially at high frequencies. You got kind of all kinds of stuff happening. So you can see why you need to model these things numerically. You're not going to bend your way through that. It's not drawing a simple dipole. We're going to measure here. And yeah, at 100 kilohertz, things look like that. At a lower frequency, you can see things are diffusing down. Same thing as in time domain. So as frequency decreases, then the information goes further into the Earth. Yeah, so let's go back to our 4-layer, for example, or multiple layers. So let's look at a resistive layer and then a conductive layer. So that's what we have with just a half space. And if we put a resistive layer in, you've already kind of got nothing much is going to happen. Conductive layer, 10 ohms, you see something there and in the top. And it's very conductive, you basically just see it in here. So it's virtually identical. The challenge with actually for me to show you images of these is that it's this whole business of currents going from the in phase to the quadrature phase, and so then it's a question of, do you plot the real part, do you plot the imaginary part, do you plot the total one? It's never quite as clean. That's why it's the time domain first. But once you've got the picture of the time domain, these things are actually really simple. And then you know that, oh, if I'm ever looking at current, then some of it could be in phase, some of it quadrature phase, but that's kind of a detail. Yeah, and there's the flux. Again, can be pretty complicated, but we're seeing out here, and there's something. This one's I think more informative in the sense. So here's our the black is the in phase or the real, red is the out of phase or quadrature, and this is a background half space of 100 ohms. If I put that 1,000 ohm layer in, the dashed lines are responsive with the layer, and you can see there's not very much difference. So resistive layer in, not make much difference. However, situation totally changes if I put a conductive layer in. So the difference between the layer in and not in is huge. That's just, well, more than half order of magnitude. Same with this. If I make it really conductive, then it goes like that. So again, same problem, or same understanding. EM, good at finding conductors. Our shielding problem, remember that's what we had for DC resistivity. Go back to exactly the same one, put a resistor in there, and for DC resistivity, if you remember, put that resistive layer in, all the currents got confined to the top, and we just didn't see this guy. Now if we do the same thing, so here's without a resistor. So at this particular frequency, you can see that there's induction in the top layer, as well as induction in the sphere. But can we see the sphere? It's good. If we put the resistive layer in, there's virtually no change. So it's transparent. And yeah, just with the resistive layer in, that looks like it was. So again, the takeaway message is that resistive layers don't bother us, and that same thing comes through on the sounding curves. So if we just look at the sphere, resistive layer, or without the resistive layer, they're pretty much about the same. Conductive layer, yeah.
The previous slide, if our target was the resistive layer,
I'm sorry?
if the target was the resistive layer,
You need to do DC resistivity.
okay.
So that's interesting. Like it depends, like what it is you're looking for. EM, you're not going to see a resistive layer, but not very easily. But you see that really clearly with some kind of a galvanic source. Differences being charges that are actually built up on surfaces because of currents trying to pass through, or whether or not you can get currents that are actually induced somehow in that layer. Conductive layer, however, as probably aware, you're hooped both ways, doesn't matter.
That's the Australian example.
That's the Australian example. Hooped. Yeah. So we've got a conductive layer up here, with DC resistivity are like this, and with the EM, yeah, just with the sphere, you see it, and with the thin conductive layer, you're just completely shielding that sphere, so you don't see it.
Not so much with the inductive example, but with the DC example. If the target was in contact with the low resistivity feature, that would change it completely.
Yeah.
Would that change it in the inductive case as well? Or not really? It's not, still not.
Well, and then it depends how much is actually, attenuating through. But if it's a high enough conductor, that's enough to screen it. Okay, so that's frequency domain EM. Completely parallels the time. The only difference is that the currents kind of get partitioned. Yes?
I was just noticing in some of your sounding curves, you can see a crossover of the real and imaginary where you have the high conductivity layer. Is that something that you look at? That crossover there, yeah.
No, actually, I never noticed it until you just asked. Well, because we're in the frequency domain, right? There's if you look at the response curve, right? So at some point, at high enough frequency, you're going to be, that induction number is going to be greater than 1. So the real part will be larger than the imaginary. And if it goes to lower frequency, it goes the other way around. So that's actually what's happening right there. Case history, groundwater. Buki. So how many people have been associated with Buki? 1, 2.
Not in this project.
Pardon me?
Prior to this work,
Oh, okay. What were you doing?
we were looking at the same area when the trees were starting to be affected by the salinity, and we wanted to see whether pumping water into the region and doing ground EM before and after was actually showing a drop or a change in resistivity near the surface, which was telling us whether the salinity was being flushed out or not, and likely to improve the condition of the trees.
Oh, it's perfect. Want to change places? 'Cause the next 4 slides are yours, right? Okay, thank you. So here it is. So here's the Murray River meandering through. So we've got an irrigation system that is up here, and the problem is salts and fertilizers and stuff from the irrigated land coming down and contaminating the region underneath here. So this is essentially kind of what happens. You get over irrigation in here and drought and water that's coming down, and you've got saline water that basically is recharging this river and causing salinization and ecological damage. And that, I guess, that's probably the iconic picture for you as far as.
And dying when you don't do anything about it.
Okay. So what happens when you don't do anything about it? So was this with CSIRO or GA
for water, land, and biodiversity, which is now Juno.
Which is what?
The Department for the department name changed, but basically it's the Department for
Okay.
Biodiversity.
So you can correct me if I'm wrong here on the story, but as it was initially sitting, you get a river in here, got embankments up here, salts that are coming in, it actually salinate the. And now, if you, the idea was to try to put in some pumps in here that would haul in this salinized water, pump the groundwater in, and then you're actually pumping it back uphill and then storing it in some ponds up here. We were a little, that's kind of what
Channeling it back inland.
Yeah.
Into some sort of basin.
You just evaporate then, or whatever happened to it?
It would. They do all sorts of analysis to try and figure out how long they could continue to pump saline water into that till they could no longer do it. And then they were thinking also about building a pipeline to actually channel it out to the ocean. That was one of the things they were considering. I don't know how far they got with that, but that was something that was on the table.
Oh,
about 10
okay.
years ago. Just to get the water back out of the area.
Right, so this is,
Stop it going into the river.
if you pump here and you're pumping water out, right, then you're gradually getting this saline water that's coming in, pump it up, put it up onto a pond up here, and kind of evaporates. This is what one of the pumping systems. Okay, so that was 2006 as far as. And then here's the result was from, I guess it was about a year. You're actually pumping freshened water near the river, and then you're to. So this region in here is a time lapse between January 2006 and March 2007, and with freshwater going in. Actually, I'm not sure whether you pump fresh water in or you just pull the salt water out.
It looks like, from that example, it looks like they did both. Now, when I was working, I think it predated the interception scheme.
Yeah.
So we were just looking at what effect pumping fresh water near the banks of the river to help those trees. Because at the time they were in drought as well, so the trees weren't getting any fresh water.
Okay.
So it looks like from the example there that the fresh and shallow water near the river is to assist the vegetation.
Yeah.
And the interception remove the saline groundwater.
I see. Okay.
There was also an environmental flow release between the two, because the survey was run 3 times. There were two frequency domains and one with skytime. So I guess what sort of restoration happened, so you can actually do the salinity through time, which is part of what is interesting about it.
Yeah. So that's kind of what this shows, right? Yeah. So this this is your resistivity as a function of depth and distance along here. You have 2 different time samples, right? And you can see that, so the blue is resistant, so think about blue as being fresh water. And then you can see that's coming into 100 meters away from the edge here compared to 50. So definitely a lot more fresh water that's come in, and all that's very positive. From our perspective here, the idea is really then to try to distinguish between this freshwater and the more conductive saline water. So the properties, basically, saline water might be, I don't know, 3 Siemens per meter, freshwater, like 100 ohm meters. And so there's a very distinct conductivity contrast. And I want to try to use that with the airborne time domain system to see. So here's the survey. 2008, it's a resolved system. I talked a little bit about this before. So it's got these horizontal coplanar. Those are the words that you hear when people say HCP, horizontal coplanar coils. So they're just about like that. They'll be separate. Each frequency is separated by its individual distance, and there's that bucking coil. You're basically measuring the ratio of the secondary to the primary. And there's also, this is called coaxial complexes. Different frequencies from about 400 to 130,000. Flowing across these lines here in the green system. So it's your helicopter, transmitter, receiver, its frequency domain. There's a magnetometer and altimeter there, and yeah, that's your system. So here's a response. I like this picture for a whole bunch of reasons, but I think one of the main ones is that, I mean, not only is it informative, I think it's something that you can use to do a personal calibration as to, okay, what have you learned during the day? So you've been here since 8 o'clock, it's a long time, haven't learned anything, right? So, okay, so take a look at this picture now. What you would have said with all of these things if you came in at 8 o'clock this morning. I'm not going to put you on the spot, but look what you now know, right? So first of all, you look here and you see these words: real in phase, imaginary quadrature phase. Okay, kind of got that. Okay, I know that my signals are going to be partitioned into those. I got some frequencies in here. I got a low frequency. I got a high frequency. So, high frequencies, oh yeah, skin depth. Yeah, so this is going to be shallow. So somehow this is all going to be shallow. That's going to be deeper. That's good. Okay, then it's a frequency domain system, right? So it's got to have some kind of, it's associated with response curve, right? So I'm looking at my sounding, right? And I'm looking at this blue part. Oh, that's the in phase part, and here's the the quadrature phase part, right? So what's going on here? Well, this guy he's really big, and he gets bigger. The higher frequency, he gets bigger. Higher frequency, this guy gets smaller. Oh, what's happening here? Oh, I remember. We're talking about this response curve. Yeah, remember this induction number on this side, right? And if I'm to, on the high end here, my real part's a lot larger than my imaginary. And the higher I go in that induction number in the frequency, parity is between these things. So that's all. I mean, that's good, right? So like you can look at this and you kind of do a little bit of a reboot calculation and say, oh, so there's got to be some really high signals, or high these high frequencies. They're good high signal here compared to here, so it's probably going to be pretty conductive there. There, I've got a certain partitioning between the real and imaginary. At lower frequencies, I'm going to be looking deeper. I mean, it's all kind of And actually, I think this is, I'm not sure what position people are in, but this is perhaps one of the biggest value items that you might be able to take away from a course like this, which is just kind of giving you the fundamentals of things, is that you kind of have an intuitive understanding about what's going on. Then you get some contractor who comes along and he's showing you some pictures and he's uttering some words. And the moment that you look at that picture and you tell him, something that's informative about what that picture is, or you catch him on a word, you just went up big time in your interaction with this guy, right? So it's important in that communication to just giving you a load of whatever, right? So, Australia. So we're going to invert these data. So here's going to be our data, and now we're going to invert each sounding, kind of stitch them together. The warm colors are more conductive. The cooler colors are more resistive. So it's starting to look something like this is the result of inverting the data at a depth of 8.6 meters. And now, yeah.
Could you just go back? I'm just looking at your data fit down there on that one.
This guy?
Yeah. Do you think you're fitting the data there?
Yeah, it's not too bad. I mean, these, that's pretty good, right? So
Are those airbuds?
sorry. So the blue is the observed and predicted for the real.
Okay.
So that's pretty good. That's good. And a little bit up there, right? And the red is the observed and predicted for the imaginary component. Yes.
So you inverted all the components simultaneously?
All frequencies simultaneously, yeah.
Both.
No, actually, this is just the coplanar. They're
And did you have to do any sort of shifting or adjustment of the data to get them, they always, and then you seem to get a lot of worms when you try to invert multiple frequencies in one go.
It's more challenging if you do the coaxial and the coplanar. I don't think we've got very much extra information out of doing that.
Any coherent
Just the coplanar. Getting through this.
Could you get any coherent information?
Pardon me? Actually, I'm not sure. We're interested in really looking up. And there is a 2015 that was up those data, but at some point I might touch base with Tim if he was around, but I'm sure Tim might be. Yeah, so the question is really, where's the fresh water going, or where's the salt going? And from conductive this way into the river, and resistive this way to the, okay, there's material here, so the general flow of how things are going. That's just my interpretation of where the salts are coming from and where they're going, and which part of that river is gaining more. The synthesis, here's the picture of the Buprana area. So here's where the irrigation was, and here's the Murray River with all of the floodplains down here. And yeah, I think it was useful, but there's also more to be had there, as I said, because there is a time-lapse element. And our impression of looking at, we've not analyzed the data, but the Aarhus group has done that a bit, and you can see definitely there's differences between 2008 and 2015. Okay, as Lieutenant Statement, you might be interested. Yeah, because Australia is interested in drones, right? So we were in Tokyo not so long ago, and it's just really interesting. So I was talking to a guy, Yuji Mitsuhara, who's head of their kind of advanced institute for geophysical technology, and this is their brochure. This is the front page of their brochure. Right? So these are the kinds of problems that they're looking at, and I thought, well, how cool is that? I mean, that's exactly the kind of thing that we would use for our discourse, right? So, whether there's oil, there's ocean, there's seafloor EM problems with respect to methane hydrate, and also submarine massive sulfides. Is that something that people are starting to think about in Australia? Does that ever come up?
What was that, sorry?
Submarine massive sulfides.
Maybe Zealandia going forward. I don't think at the moment in Australia.
The Japanese are really big on. They're probably going to start mining sometime this next year. Anyway, I mean, they're just sitting on the ocean floor waiting for it, right? So there's groundwater issues, radioactive waste disposal, geothermal, hot springs, acid mine drainage, water contamination, just kind of done that, mineral deposits, geothermal reservoirs, aquifer, CO2 sequestration, aquifer storage. So all kinds of things. And every one of those electromagnetic geophysics has a role to play. So I think it's just, shows you kind of like the potential where EM could be. Anyway, this reason I showed you this. As a as an industrial group, I mean, you want to do science. You also want it to be useful, but you also have to sell it, okay, to the government so that the government will sponsor you. Matter of doing what you want to do, couching it in a way that somebody else will kind of connect with it, right? So they had a big earthquake in Japan, and there were some landslides, and it covered up some cars. I don't know whether there was anybody in the cars or not, but anyway, there was a few cars in this village that were covered up, and they realized, like, okay, where do we, where are these, and how could we find them? So that was their mission statement. It's very explicit, something politicians could agree with, and then now you also have a project, and their idea was that, well, maybe we can make a small frequency domain system. It's kind of carried by a drone, and see where we go. So this is, again, it's the same kind of thing we just talked about, but it's now at a smaller scale. It's got its own, you can recognize them. So first of all, here's your drone, and it's going to take this little guy here, which actually looks like a resolved system, sort of. You've got a transmitter right here, got a receiver here, and you're going to tow this thing along. You need to have a certain separation between the drone and the receiver, because that's going to have a lot of electromagnetic noise that's associated with it. Here's a plot of what the kind of ambient noise when it's when your sensor here is 3 meters from the drone. That's the black. We can see it's like 1,400 parts per million, and then the red is like 600. And then by the time you get down to, if it's 5 meters away, there you have the blue line, probably good to go. So it's got to be, the drone has to be 5 meters above the sensor, and yeah, then you put it together, and now you remember too. Remember this primary field decays is one over R cubed, right? And so that's that's an issue. You want to be as close as possible. So if you got 2 cars, one that's 1.5 meters down and one that's 3 meters down, the difference between this depth and this depth is actually quite a bit when you're talking 1 over R. So we build it. Okay, they've got in phase and quadrature phase data at multiple frequencies. You know all that stuff. It's a metallic object. So metallic, immediately you think, oh, high induction number, which then means mostly, oh, it's probably in the in phase part. Amazing, you guys know all this stuff, right? So, and then you can plot just the amplitude of the field, and this is what you see. So you get something crosses here, so it's red. So that's the car at And then there's just a nice hint of a signal here. That was actually the one that's at 3 meters. The thing about it is that it's exactly the same, right? There's technological difficulties in kind of building this. The fundamentals, nothing changes. And everything that you kind of learn kind of varies. Oh, we're at lunchtime already. How clever am I? Okay. Oh, well, just to tell you what else we've got on there. Not sure if you can see this, but there's there's unexploded ordnance. There's a tutorial there for anybody who's interested. The reason that people in minerals might be interested in unexploded ordnance, you could be also interested from a mineral perspective, is that, I mean, if you take a small body, it's highly conductive, especially if it didn't have all silver. It'll actually look like a decaying conductor. It's going to act like a magnetic dipole that's decayed for transient time domain data. And that's how they find these unexploded ordinances. But that kind of thought process has been used in mineral exploration. And so there's unexploded ordinances. There's a tutorial as well as a case history. There's
I guess the question there, Doug, is what sort of sensor do you use? What system for when you're exploring like green fields to narrow down the footprint of the system, as you were saying? It's
well, you could use city. I mean,
like a frequency like that, but I guess.
Yeah, or time. You could use time domain system and just do a kind of a simple interpretation in terms of late. And Peter Fulliger has been doing a lot of stuff on that kind of like late time responses of conductive objects. Here's a case history by a really great guy in Saudi Aramco, and it's case history on Wadi Saba. Here's the use of airborne time domain EM to help refine the near surface structure to get a better velocity model for seismic interpretation. Just mention. Grounded sources. Things are getting more interesting. Okay. What I'd like to do here is to, again, we're gonna work with time domain first because that's where good intuition is involved, and we're going to look at the whole basic experiments of what happens for stuff in cold space, and then what happens in with grounded systems, and yeah, look at conductive and resistant particles. So our examples. Why are we interested? C4EM. This is actually going to be a very big topic over the next decade, because we've got all kinds of things. We've got methane hydrates. You've got C4 massive sulfides. You've got de-risking for hydrocarbons. There's just a lot of, and you've also got freshwater aquifers under oceans. They're off the coast. So lots of reasons there: methane hydrates, volcanoes, and a number of examples where you somehow want to have a grounded electrode but put in time varying current. So we get to put things together here. So we've done two things. We started off with DC resistivity, right? We kind of got that. Oh yeah, we got these these charges that are built up. It's going to give me my currents. And then we also have the inductive sources, right, where you've got vortex currents going on here. But now I want to put them together. We're going to take this configuration, but we're going to put through a time-varying current. So that actually is going to give us a combination of galvanic DC specific and inductive sources, and it's going to give us, open up a whole new kettle of fish as far as what we see for data. First of all, like electric dipole, like it's just, imagine just a little piece of wire that's connected to a generator and just plopped into the earth someplace. And a current density, just kind of go from the positive into the negative. It's a whole space, so it just kind of looks like that. And it's a dipole, so fields fall off. It's 1/r³. So let's see what happens in time. So we've got a constant, shut it off, and then leave it right there. Remember we had this formula for the diffusion distance that was kind of like how far that peak would go as a function of time. So if I turn this off at 10 to the minus 4 milliseconds, that's only 0.1 of a microsecond. It's really small. This is what the currents look like. A little bit later, diffusion distance is 13 meters. You can see what's happening to the currents. They're kind of starting to diffuse outward. And -2, later. So it's it's the kind of thing that at this point is not a surprise. You would have like basically said, well, that's what's going to happen. You put a current there. I put a current. I'm just going to leave it. What's going to happen? It's going to decay. So there's huge. You can't see the magnitudes here, but there's huge changes in the amplitude. So even though it's yellow, it's getting very, very much smaller. And you can see that the currents kind of go outward, and they just gradually decay. They just disappear. Time domain, frequency domain, doesn't matter. The only thing with frequency domain is that everything always gets partitioned into a real and imaginary part or anything. We look at the time domain. It's earlier that if you're looking here, so here's 10 to the minus 4 milliseconds, right? Time. If I'm trying to say like, okay, what would happen in the frequency? 1 over that, I get a frequency, and that would be 10,000 kilohertz. Look at the pictures of these two things as far as the currents go. The same a little bit later, and again you can look at depths and skin depths. They're kind of the same. So here's a little bit later times, lower frequencies, later times, lower frequencies. So it's same phenomenon. So that's basically it. Frequency, time, same, diffusion distance, skin depth, early times corresponding to time corresponds to the frequency. Okay? Okay, so here is where it starts to get pretty interesting. So now what we're going to do is we're going to take a current and we're going to have an A electrode and a B electrode, and we can connect that current either through a horseshoe or just a straight wire, doesn't matter. And we're going to ground this thing on the surface, but we're going to have the time, time varying current in that. And the question is, okay, how do we use that? What are all the variables, usual kinds of things that we need to think about? I think the easiest way to do that is to just take a simple example, and we'll just work through that, and then you can come back to these more individual questions later. So we're going to start with this. So we've got an A electrode here, and a B electrode here. And for DC resistivity, goes like that. That's the currents. And then we got a generator pushes it back here. So that's our circuit. Okay. This is what's happening prior to the shutoff. That's the steady state. Okay. We're going to break this into two parts. We're going to, first of all, think about the wire, okay? And kind of ask ourselves, suppose I turn that current off.
You're going to need that.
You clearly know way too much. Okay, so anybody else? What's going to happen to this? Because what was said was exactly right, but what was anybody else want to articulate? So I've got this thing set up like this, okay? So what's the magnetic field that's associated with that, right? So it's circular. It's like this. Good. Now, the moment that I turn that current off, what's going to happen?
Electric field in ground. The magnetic field.
The Earth is in a situation that doesn't like to have anything change. So it's just as we saw with that current coil loop example, right? You're going to generate currents in the ground to interact, to have any changes in that loop. So what's going to happen the moment that I turn this current off, the magnetic fields everywhere are going to be such that I have to set up a current so that the magnetic fields everywhere are the same as what they were before. So what is the most simple, intuitive way of making that current? Where does that current lie? You can't answer. Somebody else. What would you expect? John?
The opposite direction that it was flowing before.
What? It's going to go this way?
Yeah.
Okay. Who says it's going to go that way? So it goes the opposite direction.
Oh, didn't say. I've got to maintain the current.
Exactly. So the easiest way to maintain the field from this wire is to have a current that exactly parallels this wire sitting right at the surface of the Earth, assuming this guy's on here, right? So this is a fundamental thing about this. I turn this current off. If I'm sitting up here, I see no difference. The moment that current's turned up, I don't see anything different. And why is that? Because there's a current in the Earth in that field exactly. So there's going to be an image current. Well, it's actually a real current that's set up inside the Earth that now exists. Okay? But this is a real current. This is a real current inside the Earth. And now what's going to happen to that? It's going to decay. It's going to decay, just like the dipole. Remember that dipole, right? We put the dipole in, little current, and it goes. So now we kind of got it, right? I got to turn the current off, and then instantly there's going to be another current on the surface of the Earth that looks exactly the same as this initial current, but it's now inside the Earth. And then if I don't have any forcing now for that, it's just going to dissipate. So That's what's going to happen. After turnoff, I've got this current here. It's just going to kind of diffuse downwards, outwards, and eventually damage. So that's this current. Okay, that's my wire. Okay, what about, I also have these currents. So what's going to happen with them? Anybody?
Will it be the same?
Pardon me?
Will it be the same?
The same being,
Well, you initially have a current following the same path to maintain that field and then it'll diffuse out.
perfect. Yeah. Yeah, so now that I don't have any forcing here, I'm starting at some initial condition, there's the currents, and then we're just going to diffuse out. So they're going to go like this. So at the end of the day, I've got two things that are going on here. I've got higher path, and then I've got the ground currents. Two separate things, but they're both going to interact and produce measured circuits. Half space. So this is a cross section. That's kind of new. So this is a cross section. So here's A, here's B, and so you can see how the currents are flowing through. And this is what happens the moment that I turn this off. You can see the buildup of currents there. Up here, later. So again, just that whole concept. Okay, so now we know half space. Target here. That's more complicated. So take the same block in here, put in a conductive block, and intuit our way through what's going to happen here. So the current goes in like this, activity. We put a positive current in here. It's going to go through here. Remember, so it's going to be a negative charge on the side, positive charge here. There's the loop. And it looks pretty good in the sense that field is going around, and if I've got a phase of so I've got a line over here. My magnetic field is coming in like that. So that's great. That's good coupling, right? So the moment that I turn that off, I'm going to get currents inside here that are going to try to oppose that. So I'm going to not only get a vortex current, but I even know which way it's going to go. It's going to go in that direction. So I'm going to get currents then that are flowing in here. So those are my vortex currents. And at the same time, I'm going to get galvanic currents that are still flowing through. So let's see if that works. So we've got our conductor in here. And you can see it's conductor too, right? Because I put something in, it's sucking the currents in, so it's a conductor. I turn this off at an early stage. Fusion distance 80 meters in here, so that's kind of one diffusion distance. So the fields have kind of sort of decayed into here, and you can see my current lines. So now we've got these vortex currents that are inside the block, and the largest extent of the currents is sort of right up at towards the surface. A little bit later, they're going to start to diffuse inside, and now we've got kind of late time full vortex currents that are generated there. And Yeah, and then a little bit later, they start to disappear because they're, there's currents are I squared R, right? So R squared, whatever. We're starting to lose, get converted into heat, and we're gradually losing all of those currents. So this is what happens here. So we've got a block in here. Initially, we just have these galvanic currents. Then a little bit later, we get kind of vortex currents that are primarily going like this. And then back a little bit later, as these things have decayed out, if we look at our currents, you can see basically the current lines are kind of going through here. So we're a heavy response from the galvanic current. So there's charges that are being built up. So we've got both a combination of currents going through as well as vortex currents. Okay, so that's good. Now we understand, right? We've got a good understanding about how the currents are going as a function of time and what's happening. Okay, you've got a limited budget. What are you going to measure?
What are you going to make?
Yeah, I'm not sure. I can't have you answer this question because you're going to tell me the right answer. Anybody? Okay, we got. What's our possibilities? What kinds of things? We're doing an EM survey. What kinds of things could we even think about measuring?
Could be measuring magnetic field.
Could be measuring magnetic field. Magnetic field is a vector in a particular component. Pardon me?
X.
So our X component is going to be in this direction. Okay, so going to measure HX. Anybody? HY. Can I ask why you chose X or why you chose Y?
Measure the three of them.
Now you got a limited budget. Wow, I'm just. Yeah. In practice you would, right? But where are you going to see your signal?
I think you want to, HY will give you the orientation of the picocurrent that's going around the line. The surface is still in the plane from left to right, and that seems to be more excited as a secondary current within the body. So that's what you want to measure. And more than HY.
I liked your thought process. But let's take a look at this. So for the stuff from the wire, okay, let's suppose we're right at top of the wire. Okay, then what's the component that's going to be maximum from here for the magnetic field? It'll be the component that's coming, perpendicular to the wire out of the door, right?
It's going to be 7 in line.
Yeah, so that's right. So the magnetic field from the wire, okay, is like that. So there's a Z component, and then there's right above here, there's just a Y component. So that's good. So what about these guys? Okay, so those are also circular currents, right? And they're going to give also rise to magnetic field that's in that direction. So both the vortex and these guys here all say, HY would be good, and perhaps HZ, so that's good. What about E? I'm sorry?
So E from the box is the conductor, right?
Yeah.
Isn't it say like it's going in? Just
E from the box is going up. Anybody else? Can we measure? Okay, go ahead.
So similar thinking again, I mean, if it's really the E field that is connected to the current itself, if you were to switch it off, you start from the wire, it will go down, so it still has the X direction. So you're starting charges on the left and the right hand side. So again, EX is the one which has the largest galvanic offset.
Right. So EX is kind of parallel to that. So we've got EX is in this direction, right? And with respect to the vortex currents, okay, they're going like this. So at the top, there's still EX, right? EX has got to be good. And then in conjunction with that, HY, and as we come out of here, HZ. Okay? Good job. Gold star. So let's take a look. So here's EX. So here's our responses. And then if you look at the conductor, it looks something like that. It's a bit different, but you really start to see this sweet spot. So this is primarily caused by the vortex currents in the block. So we've got this very distinct anomaly here at 1 millisecond and holds up to 10 milliseconds. So EX would be very diagnostic here. And then, as we already talked about, BY coming out is also diagnostic. So here's getting half space, here's the conductor 1 millisecond, it looks like that, 10 milliseconds. And BZ, not diagnostic directly over top, but certainly as you get up towards the sides, you definitely see something. So the components are going to go out. You don't know what the orientation is, your transmitter wire to the stuff and all that. So you're probably all can measure all 3 components. But from the point of view of kind of understanding things, that this is actually good. Okay, now let's put a resistor in. So now what's gonna happen? Anybody care to speculate?
Where you get your charges built up on the opposite side for a start.
Good. Yeah, no, that's good. That's good. What about our vortex currents and stuff like that? No, so we're not going to expect anything, right? We've already kind of figured out, like, okay, we're not going to get vortex currents. Let's see what happens. So one is a city state, and here is early time. So you can see the fields kind of diffusing down and starting to interact with this body. And so everything is just kind of going down, and we just get these currents that are coming through like this. So here's the current. There's just horizontal galvanic. Each time we do this, we're going to get charges, but that's where the currents are. So in this case, so we've got a resistor, no vortex currents, everything just kind of flips down. We just have galvanic currents. Yeah, that's okay. What about data? What should we now measure? So your name is? Kate. What's your name?
I don't know, I just speak it.
Okay, anybody?
A lot of what is measured the EX field.
Sounds pretty good to me. we definitely want to measure EX, right? Because there's nothing particularly different here, right? So we're going to have charges that are built up even on these images here. Where's the currents? Currents are going through here. They're being deflected around, which means that there's charges built up on here, which means EX is, that's going to be a good thing to do. So that's EX. No question about it. That's your strong suit. Magnetic fields. There's not any vortex currents. No, there are magnetic fields that are associated, but there's not much. There's not much there. And there's your VZ. So in all of this is that if I've got a conductor, like E fields and B fields are going to be pretty good. If I got a resistor, electric fields are probably going to be the one that's diagnostic. Are going to have space. So if now you think about the big thing that hit the hydrocarbon industry a decade ago, with C4EM. The canonical example for C4EM is you've got this background ocean, and then you've got a hydrocarbon. So the background ocean sediments are 1 ohm meter, something like that. And hydrocarbons are more like 100 ohm meters. So you got a resistor that's buried in there. So immediately, the potential of having all of these different kinds of surveys, galvanic, inductive, right? I mean, you're going to step up to the top of the class and say, wait a minute, guys, what do you need? And you're going to, galvanic or inductive? Galvanic, right? And yeah, if you're going to have a ship and you're going to transmitter, that's a reasonable configuration for. Yeah, cable that you're just dragging along. You can do that, right? So you just drag a cable. You put a transmitter here, got electric fields that are in the same direction. As long as it's long enough, and that's the problem, right? Because if your hydrocarbon is depth, your array length has to be at least 3 times that. So you're going to need a 9-kilometer cable, which they do. And they string around. But that's the basic experiment. And this is why. So that was like kind of like tough enough, right? Like, okay, we're kind of screw around with your head. It's like, okay, which way is everything going? And now you find. Remember, we were talking earlier about coupling, right? So what's the relationship? How do I want to orient? How do I want to orient my plates with respect to things? And here's where it's pretty challenging quickly, right? Because we've got vortex currents, we've got galvanic currents. This is a good. I mean, you can tell intuitively this is probably good, right? Because we've got lots of coupling with the EM part here, and we've got stuff we know we can find a plate like that. And it'd be a bit more challenging to figure out if that's going to be very good. You'd say that doesn't look too promising, right? Because I don't have very much flux that's here, so that's poorly coupled electromagnetically. And then I've got stuff that's coming through. Well, I know I can find a little bit of a plate here, but it's not the ideal thing. You think, okay, that's probably poor. That's probably good. But honestly, at some point, if you get to this point, you've kind of got the principles, and you've done a few right-hand rules and stuff. I guess about certainly as far as I can go. And then at this point, you're just like, okay, just appeal to numerical modeling and do some forward simulations and see what you got. I'm going to do two case, well, I'm going to do one case history. We'll do it quickly. And I want to do one thing here on DC EM. I think that'll be of interest to you. It's a synthetic, but yeah, I think you'll find it interesting. So this is, how many people know about the deckhand traps and why they are interesting? Yes?
Yeah, I mean, I just know from literature, I mean, obviously covering a big area and then, you know, they got mineral occurrences perhaps underneath, so there's a lot of studies. I mean, I know, for example, MT definitely, they look at the deckhand trap and what's underneath.
That's right, yeah, so there's both minerals and there's also potential hydrocarbons, there's sediments underneath.
And I guess from my point of view, perhaps, I mean, because you have this volcanic cover that is got a very different to your typical sedimentary cover. We have something similar in South Australia, they call the range volcanoes.
Oh, yeah.
So there's a massive area which we call cover, but it's not a sedimentary cover. And it overlies, I mean, you said before the overlying sediments here, but in our case, the overlying basement. The trouble is obviously, you know, do they have any physical property changes across them, and so on. We haven't really been successful with a wide range of geophysical techniques.
Oh, that's very interesting. I thought all of Australia was covered with.
Almost.
So this, where is this?
This would be about 4 or 5 hours northwest from the central part of the Boulder Craton. So it covers quite a large part of the Boulder Craton.
Oh, okay. Good. So any other reasons why you might have heard of the deckhand traps or why they're interesting? Anybody know when they came up? The geologists? Recent's a very relative word. Oh, relative to Australia. Oh, recent. Oh, anybody? Oh my goodness. Oh, somebody's got, okay, somebody, deckhand traps. I mean, hugely important geologic event. Yes. Yeah, so there was, so there was a very large discussion, controversy, that felt that the deckhand traps were actually responsible for killing the dinosaurs. Happened about the same time, 65 million years ago. And the reason that there's some reason that might be true is that like millions of cubic kilometers of basalt came out, and with it, enough stuff to really alter the climate, so that animals, things could just die out with that. I think the general consensus is now that that was not really the responsible for killing dinosaurs. It really was the big meteorite impact. But both of those occurred pretty close to the same time. And so the details about whether there was some stress from the degassing and stuff of the deckhand traps that kind of marginalized the humidity or not, and whether the impact was the final blow or whether it was the cause. I think maybe there's still discussions a bit about that, but most people now think it was the impact. However, well, I'm glad to know that there's at least one reason, area in Australia that's got volcanic cover, and there might be stuff underneath, so that makes this at least a little bit relevant. So here's the scoop here. So it was the area here. Here's India, and then it's this region in here that they've got these basaltic flows over top. of sediment, and the goal is to try to where the sediment is. So they did a DC resistivity survey across this part of India, interpreted that, and they got region of basalt, big sediments, and something basement underneath. But whether the sediments under here really existed or how thick they were is kind of undetermined. So they decided they'd do something else. So they did something called a low temp, long offset time domain medium. And it's a grounded dipole, just like we've been talking about. And you measure data away from here, and you can measure both the magnetics and the electric fields. So what they did is they had a number of that were like this, and then the goal was to invert these and find out what they could say about the salt thickness. Kind of set the scene that they could actually see something. They had sort of a background model, so traps themselves sort of sediments are low resistivity, and then basements high resistivity. What you're looking at here is kind of a plot of the data, but it converts both the early time and the late time to an apparent resistivity. And the early time data follow this side, the late time data follow this. And the only thing about these curves that if you change the thickness of the sediments, then you change these curves. In other words, with this model, you could be sensitive to the thickness of the sediments. And similarly, you could also be sensitive to if you had a fixed thickness, as you just change the conductivity or resistivity of sediments, you could also see some manifestation of that. So that was just kind of part of this is a little bit of a long time ago, so it's not quite what you'd consider to be up to snuff these days, but it's good. I mean, thought processes. Yeah, the data, you stack them a lot, and you end up with things that are pretty repeatable, so there's not a lot of noise on the data. So you know what, okay, data's fine. Inverting them just in terms of 1D on profiles, like this line here, we've got salts up top, and then we've got sediments here. So this is 16 meters, that's more like over 100, and that's a couple thousand. And so along this line, you get thick sediments. As you come down through R, you get so thick, and it's got an interesting feature here. G is somewhat thinner sediments, and then by the time you get down to K, it's like that. So the upshot of this is that from these measurements, you've got the realization, the sediments are actually thinning as you go towards the south, which interestingly enough was exactly the opposite thought. People have thought, no, the sediments should increase in thickness as you go here. And I think maybe that's major things to have come out of here with respect to being able to map the thickness of those. It's an extra feature here. Could generate what's called a conductance map. So the conductance is the conductivity and thickness. So if I take a plate of conductivity 1 ohm meter and it's 10 meters thick, it's got a conductance of 10 Siemens. So here you can make a conductance map, and this region in here is a region of the highest. So then the sediments have got, okay, we're going to drill there. And they did that, so they drilled, and here is what the interpretation was, that you get X number of meters, I guess that's about 1,300 meters of basalt, and then a couple of kilometers of sediments, and then basement basalt. And they, on the drill well, they actually got something that was same. So here was the Deccan trap basalts, these sort of entry packet, and then here was basement. So simple model, but it's sensitive to it and kind of got the right idea. I mean, clearly you could do much better in this case, but it was a long time ago, and it shows the usefulness of the technique, and I think kind of a nice case history. The other reason that we chose this is because it's a different scale. It's like a bigger scale. It's a little bit more of a kind of a tectonic scale as opposed to a mineral deposit scale. I'll show you this. This is a on DC resistivity and EM, which I'll show you because it's a case where typically people would tend to throw away data, but if you measured these data actually to account for it, there's information in it that's really quite useful. So here we are. The standard waveform for DC resistivity is something then that looks like this, and what we generally see in the DC resistivity experiment is that if you don't have any chargeable material, then the voltage drops immediately to 0. Here's a case where if we've got an on-time data for our resistivity experiment, we're going to work in a horseshoe type of environment, and we're going to turn the current off, and then the voltage that we're going to measure is actually something that's going to go down. It's going to go negative, there's going to be transient, and then it's going up. So this is really considered to be noise in DC resistivity and IP experiments, and it tends to be thrown away, but if we record that, we can actually try to somehow make use of it. So that's kind of what I'd like to show you. So we've got a gradient array. So we've got an A electrode, a D electrode, and we've got current that is going to go around the horseshoe. We've got 4 blocks in here. This one is just the same conductivity as the background. This one's a very conductive block. It's a moderately conductive block, and that's a resistive block. So 4 different blocks, and we're going to just have one current source, and then we're going to measure electric fields in bipoles across this whole region. First step is to look at the DC resistivity data. The voltages look like this. If you convert everything to apparent conductivity, then you actually see a lot. You see a lot of information. You see, okay, there's a conductive block here, perhaps a block there, and a resistive block there. Yeah, that's good. If you look at the off-time data after having turned everything off, you start to see the following. And now I think we've seen enough of the EM induction. But this is now starting to make sense, right? Because we've got this wire that's going up here, and we turn it off, we're going to be most sensitive to what's going on close to that wire, and then those fields are going to kind of diffuse in, but then they're going to hit this conductive block up here, so they're not going to get channeled through there very easily because it's difficult to penetrate. But then we get currents that are going to be in that block. They're going to vortex currents. Everything's going to hang around for a while, and then they're going to kind of gradually decay. So you can see there's lots of information. We've got 4 different time channels. Things are happening. We should be able to get something really useful out of that. If we look at decay curves at these 3 places, A1, A2, A3, the black line is the blue line is the reference half space, and the black line is the response sitting over here on A1. And here's A2, and here's A3. So we've got decay curves then for each of those. You can see that there's really not much happening for A3 as far as that's that resistive block. So whether it's there or not doesn't do very much. But A1 and A2 definitely see something. So we got the DC data. So we could go ahead and invert them. That would be just the same thing as we did first thing this morning. And we're going to go ahead and invert them. But we have a little bit of a challenge here because we only have one transmitter. So that means that the DC resistivity data from a gradient array are kind of like a potential field. It's just kind of like inverting magnetics data or gravity data because you only have one source that's associated with it. So in order to really make any real progress in that, we actually have to put a depth weighting in. With inverting magnetic data, remember there's a 1 over r cubed drop off of gravity data 1 over r squared. You have to put that into the, well, it helps a lot if you put that into the inertia program and then balance out that sensitivity. So here's the truth. And if we do that 3D inversion and do cross sections, see, okay, I've actually done much better. I've got the conductors here. That one's a little bit bigger than this one. That looks like a resistor. Here's the cross sections. You know, not bad at all. Is that one? Yeah.
With the depth weighting that you apply there, how much topography would you need on the surface before you need to then apply distance weighting rather than depth weighting?
Oh, that's a hard question to answer in general. Yeah. That's hard. We can do some simulations. That would be much easier.
Yeah.
So here's what, I mean, you could also take these same data. Remember now we've got all of these different sections at different times. So we can take those are data, we can invert them, and this is what we get out from that. So actually look at this. And the thing about this is that there's no depth weighting. Intrinsic resolution here by having different time channels. So that's telling us different things, different times. So that, I think, is really interesting. If we look at what we get out of this, we've actually got arguably a better conductivity model that comes out of this guy than we actually had before. So my point here is that a true model, we can do things from the DC resistivity. We never want to throw those data away. At the same time, we've got data that we used to throw away. It has really valuable information. So what's required here is to make sure that you record early enough in time to try to capture this. So when you're doing a DCIP experiment, very often you're thinking like, oh, the IP part, like that's not going to come until here, right? So I'm going to not sample my early times very rapidly. But if you do that, so if you sample this stuff really early, gamma effects, you're not really seeing that's associated with it. That's really valuable information. And all you have to do is sample more, and then you capture that, you can work with that, and then that combination of the conductivity model that's obtained from the inductive part, as well as maybe even the conductivity model from DC, that's going to help you tremendously in unraveling the data and inverting for the IP response. So this is completely underutilized at this point. but it requires that people just start to realize, like, even though I'm really interested in a long-term IP effect, that there is going to be some advantage to recording these early times. Okay, we need a break, so let's have coffee. 3 o'clock, that's when they said coffee was. Yeah, I think so. That'd be perfect. And then, yeah, do that, and then I'll just tell them a little bit about what exists. Yeah. Everybody understood, we can do that tomorrow. And then we can simply go to the end. Oh, the RP. Yeah. 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 That works. Least I can do. All these things are just artificial.
But we also But you know this stuff, right?
As usual, 3 times I've been here this year now. Maybe 2. I've got one too, I'm better go back to
I bet you were leisurely.
I've got to run there. It's not going to be when I get there. We're going to run there. Written on my bags for us. Spread out. I can't wait to see next to Rob. I'm more of a receiver. Let's try. Oh, yeah. I love everybody where voices. When I was next morning, easy to find out who did it.
Okay, so guys. Yeah, yeah.
North Terrace.
Is that far from here?
Okay, good. That's easy. Okay, good.
Oh, thank you. Oh, thank you. Oh. Sometimes do. It might be okay.
If you get stuck again, help you out. Really wrong.
Oh, I see. Okay, can I get everybody to take your seats, please?
What's it? No, it's fine. We'll give you. This was flat. Oh, okay.
Please might they want to the back.
Oh, yeah. Perfect.
Have you guys gotten movies yet?
These are just feedback form for today. Feedback. Yeah. What's this?
Very good.
Okay, guys, listen up. Run the whole switch. So there's a couple of things. First of all, there's some feedback forms that are coming back. We greatly appreciate if you go to these guys out sometime before the end and have them in. Appreciate it. Secondly, okay, here's a plan. It is now Simpay. So we need to at least open their eyes as to what exists. Then what I'm going to do, I'm going to continue on talking with sections. That we've been developing, like EM GeoSci. So we've got a website started called GeoSci.xyz.